There is a flash of light, if you can even call it light, that left its source before complex life had even crawled out of Earth's oceans. It traveled, uninterrupted, in a straight line through the expanding fabric of the universe itself for over 8 billion years. And on its way here, almost as if the universe wanted to make absolutely sure we wouldn't miss it, that signal passed directly behind another galaxy, one that had nothing to do with where the signal came from, a galaxy that just happened to be sitting in exactly the right place, at exactly the right moment, to bend space-time around it like a cosmic magnifying glass and throw that ancient signal directly at us, amplified. This isn't science fiction. This happened. It was detected. And the team that found it, led by a South African astrophysicist using a radio telescope array in the Karoo Desert, just gave it a name that sounds like it belongs in a comic book. A Gigamaser, not a Megamaser. A Gigamaser. Because what they found broke the previous record so thoroughly that astronomers needed an entirely new word for it. By the end of this video, you'll understand exactly what a Gigamaser actually is, why this particular one required 2 separate, almost impossibly unlikely cosmic coincidences to even be detectable at all, and why a team of scientists in South Africa now believes this single discovery is just the first of what could eventually be thousands more, each one a kind of fossilized snapshot of the most violent, most creative process in the universe. 2 galaxies colliding and being reborn as one. Let's start with the basic shape of the story, because the details matter enormously, and a lot of the early reporting around discoveries like this gets the scale slightly garbled, so it's worth being precise from the very beginning. In early 2026, an international team of astronomers, led by Dr. Thato Manamela, a postdoctoral researcher at the University of Pretoria in South Africa, whose work is funded by the South African Radio Astronomy Observatory, announced the detection of an extraordinarily powerful radio signal coming from a galaxy system designated HATLAS J142935.3, sometimes shortened to H142935.3 for convenience. The signal had traveled for more than 8 billion years before reaching the MeerKAT radio telescope array in South Africa's Karoo region, one of the most sensitive radio observatories on the planet. This means we are seeing this galaxy system as it existed when the universe itself was less than half its current age, a snapshot from a cosmic era astronomers often refer to as cosmic noon, the period of peak galaxy formation and star birth in the universe's history. The findings were significant enough that they were accepted for publication in monthly notices of the Royal Astronomical Society Letters, one of the most respected peer-reviewed journals in astronomy, the kind of publication that doesn't accept claims lightly. Now here's the first genuinely strange detail worth sitting with. This signal isn't visible light. It's not something you could see with your eyes, even with the most powerful optical telescope ever built. It's a radio wave, specifically tuned to a wavelength of about 18 centimeters, produced by a molecule you've probably never thought about before in your life, hydroxyl, a simple combination of one oxygen atom and one hydrogen atom, written by chemists as OH. And under very specific, very extreme physical conditions, clouds of this hydroxyl gas can do something that sounds almost too elegant to be a natural phenomenon. They can produce a laser, not a metaphorical laser. An actual, physically real, coherent beam of radio wavelength radiation operating on exactly the same fundamental quantum mechanical principle as the laser pointer you might have used in a presentation, just at a completely different wavelength, and on a scale that would make any human engineer weep with envy. To understand why this matters, we need to take a brief detour into how a laser actually works, because the comparison astronomers are making here, calling this a cosmic laser, isn't just a catchy phrase for headlines. It's a real, precise, technically accurate description. A laser, whether it's the one in a laser pointer, the one in a DVD player, or, theoretically, the one occurring naturally inside a colliding pair of galaxies, works through a process where a large group of atoms or molecules gets pumped into an excited energy state, and then, triggered by a passing photon of just the right energy, releases its stored energy all at once in a synchronized cascade, producing a beam of light that is remarkably focused, remarkably pure in its wavelength, and remarkably intense compared to ordinary, disorganized light sources. When this exact same physical process happens naturally in space, using microwave or radio wavelengths instead of visible light, astronomers call it a maser, a word built the same way laser is, just swapping out the L for an M, standing for microwave amplification by stimulated emission of radiation rather than light amplification by stimulated emission of radiation. Masers, in general, are not new to astronomy. They've been studied for decades, and relatively modest ones have even been detected within our own galaxy, in star-forming regions and around certain types of aging stars. But there's a special, much rarer category called a megamaser, where the conditions become extreme enough, typically inside the chaotic, gas-rich, turbulent environment created when two entire galaxies collide and merge into one, that the resulting maser emission becomes millions of times more powerful than anything that occurs in ordinary, undisturbed, star-forming regions. And then, sitting above even that already rare category, is the term this discovery forced astronomers to formally invoke, Gigamaser. According to the researchers, Gigamasers can be billions of times brighter than an ordinary garden-variety maser. The energy output required to produce something at that scale is, in the words of one of the science writers covering this discovery, the result of an unfathomable cosmic furnace. And in this specific case, that furnace is the gravitational violence of two entire galaxies smashing into each other and slowly becoming one. So let's talk about that furnace, because the underlying physical story, what's actually happening inside HATLAS J142935.3 to produce a signal this extreme, is genuinely one of the most dramatic, large-scale events that occurs anywhere in the universe. Galaxy collisions are not, contrary to what the word collision might suggest, sudden, instantaneous events like two cars crashing on a highway. They unfold over hundreds of millions of years in extraordinarily slow motion by human standards, as two galaxies' gravity gradually pulls them toward each other, distorting their spiral arms, flinging long streams of stars and gas out into intergalactic space, and ultimately drawing their cores together into a single, larger, often dramatically reshaped galaxy. During this process, something crucial happens to the vast clouds of interstellar gas, primarily hydrogen, that exist throughout both galaxies. As the two galaxies' gravitational fields interact, these enormous gas clouds get violently compressed, squeezed together far more densely than they would ever be in an undisturbed, calmly rotating galaxy. This compression triggers what astronomers call a starburst, an intense, often extraordinarily rapid episode of new star formation, sometimes producing new stars at a rate dozens or even hundreds of times faster than a typical, calm galaxy like our own Milky Way. This newly formed burst of young, hot, energetic stars floods the surrounding compressed gas clouds with intense radiation, exciting the hydroxyl molecules within those clouds into the specific excited energy state required to produce maser emission. According to the research team's analysis, the complex emission profile detected from this particular system shows what they describe as a remarkably high signal-to-noise ratio, essentially meaning the signal came through loud and clear despite the staggering distance it had to travel, which is itself a strong indicator of just how violently energetic the underlying merger actually is. Researchers studying the system have noted that, structurally, this distant collision bears a striking resemblance to a far closer, much more extensively studied galaxy merger that's practically a celebrity in astronomy circles. The Antennae galaxies, a famous, currently colliding pair of galaxies located a comparatively nearby 45 million light-years from Earth, often used as a textbook example of what galaxy mergers look like in their most active, chaotic phase. Now, here's where the story takes its second, equally important turn, because the sheer distance involved, more than 8 billion light-years, raises an obvious and important question. How did anyone manage to detect this at all? Signals get fainter the farther they travel, following the same basic physics that makes a flashlight beam dimmer the farther away you stand from it. At a distance this extreme, you'd expect almost any signal, however powerful at its source, to be diluted down to something essentially undetectable by the time it reaches Earth. This is where the second cosmic coincidence enters the story, and it's the detail that turns this discovery from merely impressive into something the research team itself describes as wonderfully serendipitous. Sitting directly between Earth and this distant, merging galaxy system, by pure chance, is an entirely separate, unrelated foreground galaxy. This intervening galaxy has nothing to do with the Gigamaser itself. It's simply, by sheer cosmic coincidence, positioned almost perfectly along our line of sight toward the more distant system. And because that intervening galaxy has mass, and because mass curves the fabric of space-time itself, exactly as Albert Einstein's general theory of relativity predicted over a century ago, light and radio waves passing near it get bent, focused, and magnified in a phenomenon astronomers call strong gravitational lensing. Dr. Manamela offered a particularly vivid, accessible way of understanding this effect, comparing the foreground galaxy's lensing influence to the way a single water droplet sitting on a window pane will bend and distort the light passing through it, magnifying and reshaping whatever is behind that droplet, purely as a consequence of the droplet's curved shape interacting with light. In this case, the foreground galaxy's gravity is curving the local geometry of space-time itself, acting as an enormous, naturally occurring lens, sitting perfectly positioned between Earth and a target 8 billion light-years farther away, amplifying that target's otherwise impossibly faint signal into something MeerKAT's instruments could actually pick out clearly from the background noise of the universe. So the full picture looks something like this. An extraordinarily violent galaxy collision, more than 8 billion years ago, produced a record-breaking burst of maser emission. That emission traveled, uninterrupted, across more than half the entire observable universe. And purely by chance, an entirely unrelated galaxy happened to be sitting in exactly the right spot along the way to act as a natural telescope, bending and amplifying that ancient signal just enough for a radio array in South Africa to finally catch it in early 2026, more than 8 billion years after it was first produced. It's worth pausing here to genuinely appreciate just how improbable this entire combination of circumstances actually is, because it's easy to read through these details quickly and miss exactly how many things had to line up correctly for this particular discovery to even be possible. First, you needed a galaxy merger violent enough and gas-rich enough to produce maser emission in the first place, already a relatively rare category of event in the broader population of galaxy collisions happening throughout the universe. Second, that merger needed to be powerful enough to produce not just an ordinary megamaser, but specifically a record-breaking gigamaser, putting it in an extremely small, elite category of the most extreme examples of this phenomenon ever recorded. Third, an entirely separate, unrelated galaxy needed to happen to be sitting almost perfectly along the precise line of sight between that distant merger and Earth, positioned with a kind of geometric precision that, across the vast three-dimensional volume of the observable universe, is genuinely rare. And fourth, humanity needed to have already built an instrument sensitive enough and pointed in the right direction at the right time to actually catch this amplified signal when it finally arrived. Remove any single one of these four factors, and this discovery likely never happens, or at minimum, never gets detected with the clarity and confidence described in the published research. This is part of why the discovery team has been notably careful in their public statements to frame this not as a one-off curiosity, but as a demonstration of capability, a proof that this kind of detection is achievable at all, with the explicit hope that it represents the first of what could eventually become a much larger, systematically studied population of similar objects. This raises a genuinely important question worth addressing directly. Why does any of this actually matter, beyond being an impressive, headline-grabbing example of how sensitive modern instruments have become? What does a single gigamaser, 8 billion light-years away, actually teach scientists about the universe? The answer connects to one of the deepest, most actively researched questions in modern astrophysics. How did galaxies, including our own Milky Way, grow, merge, and evolve over the roughly 13.8 billion-year history of the universe? Galaxy mergers aren't a rare, unusual exception to how galaxies behave. They're a fundamental, central part of how essentially every large galaxy in the universe, including our own, has grown and evolved over cosmic time, through repeated collisions and absorptions of smaller companion galaxies across billions of years. Studying megamasers and gigamasers gives astronomers a uniquely precise, almost surgical tool for examining the specific physical conditions inside these mergers, the density, temperature, and dynamics of the gas clouds being compressed, the intensity of the resulting starburst, and potentially even clues about the behavior of the supermassive black holes that sit at the center of nearly every large galaxy, since some research has connected certain megamaser systems to the presence of dual, actively merging supermassive black holes within a single colliding system. Crucially, because the light and radio waves from this particular system have been traveling for more than 8 billion years, what we're observing isn't a recent event. We're getting direct, observational access to what galaxy mergers actually looked like during cosmic noon. The period, roughly 8 to 11 billion years ago, when star formation across the universe as a whole was at its most intense, most prolific peak. Studying systems like this gives astronomers an increasingly detailed, increasingly precise picture of exactly how that critical period in cosmic history actually unfolded, observed directly, rather than reconstructed purely through theoretical modeling and simulation. Before going further, it's worth being completely transparent about the current state of scientific certainty and uncertainty around this specific discovery, because honest science communication means clearly separating what has been confirmed from what remains an open, ongoing area of investigation. The detection itself, the radio signal, its wavelength, its strength, and its association with the HATLAS J142935.3 system has been confirmed through peer review and accepted for publication in a serious, reputable astronomical journal, which represents a meaningful, real threshold of scientific scrutiny. The classification of this system as the most distant and most luminous hydroxyl-maser detection on record, warranting the new term Gigamaser, is the team's own formal scientific conclusion, based on careful measurement and comparison against the existing catalog of previously known megamasers. What remains more open, more actively debated, and more genuinely uncertain includes the precise internal structure of the merger itself, exactly how the two original galaxies were configured before colliding, the exact role, if any, that supermassive black holes at the centers of these merging galaxies might be playing in the broader picture, and, perhaps most importantly for the discovery's broader significance, whether this genuinely represents the first detectable example of a much larger population of similar gigamasers waiting to be found, or whether it might instead be an unusually fortunate, comparatively rare combination of circumstances that won't easily be replicated again soon, Dr. Manamela and the research team have been explicit that they view this as an opening chapter rather than a singular curiosity, expressing hope in their own public statements of eventually identifying hundreds and ultimately thousands of similar systems using the continued sensitivity and ongoing upgrades planned for the MeerKAT array. But that ambition, however well grounded in the team's technical expertise, remains a goal for future research, not yet an established, confirmed outcome. There's one final piece of this story worth sitting with, because it reframes the entire discovery in a way that goes beyond the impressive technical details into something closer to genuine cosmic perspective. The light, or rather the radio waves, detected by MeerKAT in early 2026 began their journey across the universe more than 8 billion years ago. At the time this signal was emitted, our own sun did not yet exist. Earth did not yet exist. The entire 4.5 billion year history of our own solar system, every event in the geological and biological history of our planet, the formation of the oceans, the emergence of the first single-celled organisms, the entire age of dinosaurs, the rise and fall of countless species, the appearance of humans, the construction of every civilization that has ever existed, all of it happened after this particular signal had already been traveling, silently, continuously, through the expanding universe for billions of years, completely indifferent to anything happening back on the small, unremarkable planet that would eventually, very recently, in cosmic terms, build an instrument sensitive enough to finally catch it. And it arrived, not through some flaw or coincidence in our understanding of physics, but precisely because the universe behaves exactly the way Einstein's equations, published in 1915, predicted it would. Mass curves space-time, and that curvature can act as a lens, focusing and magnifying light and radio waves across distances so vast that human language genuinely struggles to make them feel real rather than merely describing them as an abstract, oversized number. So here's the question worth sitting with as this discovery settles in. If a single, almost impossibly unlikely alignment of two unrelated galaxies separated by billions of light years was enough to reveal a record-breaking event that happened before our own planet was even born, how many other equally extraordinary signals from equally violent, equally ancient cosmic events are passing silently through our corner of the universe right now, completely undetected, simply because no galaxy happens to be sitting in exactly the right place to bend that particular beam of light directly toward us?